This theorem uses the definition of a linear subspace, which states that if you have a set A is going to be a subspace or linear space if it satisfies two conditions. The first condition says that if you take two vectors in A that we call x and y, the sum of them must also belong to A. And the second condition says that if you take a single vector in A and any constant alpha, which is a real number, when you multiply the constant by the vector, that also must belong to A. So this here is a definition of a linear space. And the theorem that we're trying to prove is that if we have a linear space, or if we have a set that is not empty, it's going to be a linear space or subspace if and only if, which is a double arrow, when you take any two vectors, x and y, that belong to the space A, and you take any two constants, alpha and beta, so far the only difference is that we're taking two constants instead of one, then alpha times x plus beta times y will have to belong to the set. So really all this is actually doing is just combining the two conditions that we mentioned above in the definition. So this here is the actual theorem that we want to prove, and we're going to use the definition in order to do that. So formally what this is saying is that A is closed with respect to linear combinations. Meaning that every linear combination of any combination of vectors has to be in the set. So since it's an if and only if statement, we have to prove it both ways. But both ways are pretty straightforward. So for the proof, for the first part, we're going to start off assuming that we know that we have a subspace or a linear space. And if we have a subspace or a linear space, then we can use the definition that we stated above. And say that if we know that it's a subspace, then we know that, as we set up here, every sum has to belong to the set, and also every multiple of every vector has to belong to the set. So this means that alpha times x must belong to A, and also beta times y must belong to A. And then if these are two different vectors using the second property, then alpha times x plus beta times y, so the sum of them, must also belong to A. So here we're just saying that if we can individually say that the sum of two vectors and also the multiple of vectors have to belong to the set, then also the sum of the multiples has to belong to the set. Now in the other direction, it's actually even easier. Because if we want to prove it backwards, basically we start off knowing that this is true, that alpha times x plus beta times y must belong to A. And we have to prove the two properties that we stated above. So since we know that alpha x plus beta y belongs to A. First, we want to prove that x plus y must belong to A. So that's simple because we can say that this is true for every alpha and beta. So if we simply make alpha and beta both 1, then x plus y would belong to A, which is confirming that the first property is satisfied above. And then for the other property, so this one here, the second one, we want to prove that every vector x by itself, every multiple of x by itself must belong to A. So we want alpha x. And so in order for this to give us alpha x, we need to say that alpha is just going to stay alpha, but beta is going to be equal to 0. So if beta equals 0, then we have alpha x plus 0y. So just alpha x must belong to A. And so we also proved in the opposite direction that if the set satisfies this condition over here, then it must also satisfy the condition stated in the definition above. So in the end, if you know the definition of a linear space, you're just using it in both directions. And just to clarify one little thing here, I meant to write if and only if, which is if with 2 f's, which is also a double arrow. So it just means that the statements imply each other.